Good morning and welcome to round 3 of the 2021 Facebook Hacker Cup and the solution video to problem B, authorization. So in this problem we have a 2D grid of numbers where each cell in this grid represents an office or some room in Facebook's office building. Now we have a very important restriction on this grid. That's that the width of the grid is at most 3. The height can be rather large, up to like 1,000,000, but the width is very small. So we are definitely going to use that in our solution. And we want to answer a bunch of questions on this grid. Each question gives us a starting point and an ending point, and then also the authorization of the employee who's trying to get from the start to the end. We want to know if there's some path for this employee to get from the start to the end, and if so, what's the length of that path. Now, the employee has this authorization level, which means the employee can only go through rooms that have a security clearance of that level or less. So in this example, the employee's authorization level is 6, which means he can visit several rooms, but not all of them. For instance, he can't go straight up from room 3 to room, or this room to this room, because he passed through this room, which has a security level of 100, so he doesn't have clearance to see that. Now, in a spectacular turn of events, we have the ability to bring a brand new whiteboard in here and look only at the positions that this employee can see. So everything that isn't crossed out in red is what the employee can see. And from this, it should be pretty clear that the fastest path might look something like this. So the employee would want to end up going down, come over, and then wind up wrapping around. But it's possible that we want to have another query that just so happens with the same start and end. But what if L instead of 6 is equal to 10? Well, in that case, this square is now traversable. So we now have a faster path. This path visits 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 plus the 12th cell here. So it has a total length of 11, a distance of 11. But we can do something faster. We can now take this path instead. And that will save us 2 moves. So this is a little bit faster. So this will have a length of 9 instead. So that's a little bit better. And then we might have to answer a bunch of different queries. So maybe not even for these same start and end points, maybe for different levels. And the question is, how do we do this? Well, as you may have guessed, it's very helpful to look at only the squares we can traverse. So what we're going to do to solve this problem is do a sweep where we consider rooms becoming available as this happens. So we'll start with employees with no clearance level and look at only the rooms they can visit, which will be nothing. And then we'll slowly increase the clearance level. And as the clearance level increases, rooms like this will become available. And also we'll have employees of this clearance level where we need to answer this question, right? So maybe for the clearance level we're currently at, maybe we're at clearance level 10. We've just allowed all of the rooms of level 10. Now we want to know for a bunch of pairs of points, what's the shortest distance between these two? All right, so that's the idea. How on earth do we do that? Well, in an even more spectacular turn of events, I've prepared a second whiteboard with a clean grid. Let's just take a look at this. So one thing to notice here is it turns out because of this very significant restriction on the width, there aren't that many paths you can actually use. It turns out the path I used in the sample is basically the most common or the most complicated path we can do. So we can go up and over like this. Maybe we can zigzag a bit in the middle. And then at the end, we can like come over and back and come back up. But it turns out like you can only have this little U part at the top and this little U part at the bottom. This path has to be very simple. If you ever have these 3 squares, then you can immediately start coming back up. So you know, for this entire range, you know all of these y coordinates except for the bottom look the same. They all have a traversable square on the left, so you're allowed to travel in this square. You're not allowed to travel in this square, and you're allowed to travel in this. That's the only time you'll get something like this. If you want to travel all the way across, all 3 need to be traversable. And for everything above it, you need to be able to travel down and travel up, but this leftmost square won't be traversable. Otherwise, you could just travel across earlier. So yeah, we noticed we have a very important restriction on what this looks like for these top and bottom parts. And other than that, we can split this into 3 pieces. For this middle piece, we have the additional restriction that you can never, like if you imagine you're going in this direction, for this middle piece, it's never possible to end up going up. The only way you can go up is once you've passed your result, you can go straight down, straight over, and straight up, and that's it. So because this is a very simple problem, we don't need something complicated like Dijkstra's algorithm, or even a BFS for each of these things. We can abuse the fact that this is a very simple type of path. Okay, how do we handle each of these things? Well, what we can do is we want to be interested in rows that look like this, so complete rows. For the top and bottom parts, we want to find what rows are complete. So to do this, we can store, if we're in C++, we can store a set. If we're in Java, we can store some tree set of all of the rows that are full. And we can also store counts for each row, so how many things are in each row. When that count hits 3, when we're processing some square, we can say this row is now full. What that'll let us do is when we're at this position and we want to say, okay, maybe we want to consider this middle point here and this middle point here. And I guess the spoiler alert here is we're going to brute force what these 2 middle points are. There are 3 choices for the top, 3 choices for the bottom. So we know we want to travel to this middle point. Since this has a horizontal gap of 2, it's possible that we'll travel up, go across, and then travel down. If it had a horizontal gap of 1, we can just step right across, of course. And if the horizontal gap is 0, you don't need to step at all. But for this gap of 2, you want to find the first full row above you. And that's the row that you're going to use to go across. Now, once you find this row, you need to check something else too. You need to make sure there aren't any, I mean, of course, these spaces need to be not traversable, but you need to make sure there aren't any untraversable spaces here. So to do that, you can use either a segment tree or a bit, a Fenwick tree if you prefer. And you can store, for each of these x's, you can store a 1 in this position if this space is active, or if the space is like, if you can use it, or a 0 if you can't. So then you can quickly check for an entire range. Can you traverse every element in this range? Can you go all the way up? And you can do that in just log n time. So that'll tell you whether you can travel across this path. We know since this row is full, you can travel across. And then you can have another bit for column 3 for whether you can traverse this third path over here to make sure there aren't any untraversable squares on the right. So that will help us handle this top part. We can figure out how long it is and also whether or not it's possible. Now we need this middle part. The bottom part is, of course, just the same as the top, so I'll skip that. But the middle part is rather interesting. And to do this, it's interesting because we need to handle updates. So we could do just binary lifting. The problem with binary lifting is it doesn't handle updates well. So we need something more flexible. And it turns out we can use a segment tree. So basically, what you can imagine doing is constructing a horizontal segment tree. So we have like one segment tree node. Actually, it won't look exactly like this. But you can imagine taking this and then rotating it. So we have some path that looks like this. Maybe. And then we have some start here, some end here. So this is a subset of the entire grid. Maybe the entire grid looks like this. And all I've done here is just rotated this 90 degrees. But we'll have one segment tree node for this entire grid. And then just like a normal segment tree, we'll split this up into 2 halves at each layer, which means we will have log n layers in total. So I'll just draw a few layers here, just so you get the idea. But this is some representation of what the segment tree might look like. Now, if we want to process some query, what each node can store is if I start at this x coordinate and I end at this x coordinate, 1, is it possible? And 2, what is the shortest distance, assuming I can only travel down, right, and left. So we want to know for every starting x and every ending x. So there are 3 starting x, 3 ending x's. We'll store 9 values. A nice way of storing this is just in a 3x3 2D array. And then we can say, OK, if I travel across this entire node, I know for every starting index and every ending index, if I go from here to here, what's the distance? We also know that for this node here. So we can figure out, using these two matrices, for every start here and every end here, what is the minimum distance between them? We're going to have some intermediate x that we cross at, right? So you can imagine we have this line here. Maybe the first segment tree node represents these three. The next segment tree node represents these three. If we want to go from this A here, maybe this is the first x we're considering, and this is the C we're considering here, there's going to be some x where we cross at. Since we're going to go down, we're going to have to cross this somewhere. So maybe we cross it here. We might do stuff down here like this, right? It's not necessarily straight down, but there's going to be some x where we cross this. So we can brute force the AX, we can brute force the CX, and then we can brute force for each AC pair which B we cross this at. And now this is just the addition of two elements. One is in the left child, one's in the right child. And then also this one move, so we have to add 1 to our cost here as well. All right, so that's the idea for how you build a segment tree. Now when you need to perform like some query on the segment tree, it's pretty much the same thing. We just have these matrices and we have a way of combining them, just like what I mentioned here. So you have this 3x3 2D array, and you have the ability to combine two of them pretty easily. Anything else that's important here? The last thing you just need to consider is how do you update, or how do you like create this matrix for a particular row for one of these leaf nodes of the segment tree. And doing that isn't too bad. You can just manually see for each pair, can you travel directly there vertically or horizontally? If you can, that's just the distance between them. And if you can't, then the distance between them is infinity, is how I implemented it. Awesome. Hopefully that was helpful. And hopefully that helps you solve the problem if you weren't able to in contest. If you'd like to check out some solution details, I'll have a Java solution in the description of this video. And you can check out the C++ solution, as well as the better for reading editorial, if you like seeing stuff more visually rather than seeing it explained with a whiteboard. Again, that'll be in the description. And that's the official contest editorial as well. Okay, thank you for watching. Have a great day, and hopefully you enjoyed the problem set.